Well, good afternoon, good morning, everyone. Welcome to one of our special events at this year's 2021 Better Building Summit. We are here for the virtual building tours, and it'll be, I promise, a very exciting session. For those of you who don't know me, my name is Maria Vargas. I'm the director of the Better Buildings Initiative here at the U.S. Department of Energy. And if you were able to join us for the opening plenary, I teed this session up, and I want to do that a little bit here as well. When we're not in a pandemic, when we can travel, one of the things that we have really enjoyed doing at the Department of Energy is getting out and seeing our partners work firsthand. We do site visits around the country throughout the year because we want to not only see what our partners are doing and learn from them as we tour their buildings and plants, but we also want to make sure the word gets out on what people are doing so that not only folks in the communities where these buildings and plants are understand the work that's being done and the leadership that's being demonstrated within their community, but it's also a chance for others to learn from the work that's been done. Well, 2020 was an interesting year and we weren't able to travel, but the partners today stepped up and worked with the Department of Energy to do some virtual building and plant tours. And we are very excited to share with you those buildings and those plants and the work that's been done. Before we jump in and I turn it over to the speakers, I just want to remind folks of a couple things. This is a session that's being recorded and it will be available afterwards on the Better Building Solutions Center. So please check it out, or if you think this is a great session, refer your friends to listen in. And if you have any audiovisual problems or issues, please do go ahead and send a message in the chat window located at the bottom of your Zoom panel. Okay, and with that, I want to lastly ask everyone to make sure that they are logged in and using the virtual interactive platform that we're using for the summit, and that is slido.com. So you see that on the screen right now. The event code is #DOE. And of course, this session is entitled Virtual Building Tours. So without further ado, I want to turn over this really special session, which is going to give us a look into the inside of 3 Better Buildings, Better Plants partners, and turn it over to our partners to give you their tours and highlight the innovative technologies and practices that they have implemented in their facilities. The way it's going to work is that I'm going to ask each partner to share. We have a short video and some slides on each facility or each plant. And then after each of the partners speaks, we have left plenty of time for questions. So please, again, go to slido.com and type in your questions. You can also upvote questions. So if you see other questions on slido.com that you think would be great to hear answers to, please upvote those and we will try to get to all the questions that people submit. So with that, I'd like to turn it over to our first speaker today, Michelle Kroll. Michelle Kroll is an energy manager at Ford Motor Company, and she's been supporting non-manufacturing facilities primarily in Southeast Michigan. She's been with Ford almost 2 years and has held various project and operation positions. She's an engineer in the oil and gas sector. And with that, we'd like to start with a short video on Ford's energy work before I turn the microphone over to Michelle. So with that, if we can roll the Ford video, I'd appreciate it. And then Michelle, the floor will be yours. Thanks.
Great. Thanks, Maria, for that introduction and for the team at DOE for helping put together that awesome video. So let's dive into a little more detail with the Central Energy Plant at Ford's Research and Engineering Campus in Dearborn, Michigan. The CEP is a combined heat and power facility that started operation in December 2019. It serves 6.5 million square feet of research, lab, and office buildings in Dearborn, Michigan. It provides electricity, steam, chilled water, and hot water. The plant consists of 2 natural gas-fired turbines that generate electricity, each of which is coupled to a heat recovery steam generator, or HRSG, to generate steam. Excess steam can be used to produce additional electricity through a steam turbine generator, or STG. Hot water is generated through waste heat recovery and chilled water from a chiller plant. 34 megawatts of electricity is provided to Ford and the public grid. The plant employs 6 operating engineers, 1 instrumentation technician, and 2 facility managers working 24/7. Energy efficiency efforts at this facility were focused on getting as much use out of the BTU as possible, integrating the facility for multiple paths of heat recovery and multiple configurations to run equipment based on Ford's needs. Some of the innovative technologies that were used were the extensive 3D modeling in the design phase that has become the basis for the digital twin. Also the development of technology which allowed switching legacy hydronic systems from glycol to water, which is more efficient. So some of the sustainability objectives for office space were a 50% reduction in carbon footprint, a 50% reduction in water use, a 60% improvement in chilled water production efficiency, and 100% space heating from recovered waste heat. So if we start our tour at the east side of the plant, the top left corner there, you can see this is the main entrance, and you can see those really large windows that provide a lot of natural daylight, which is unusual for an industrial facility. And the building itself is LEED Gold certified, as you saw in the video. If we walk around to the north side of the plant, you can see the thermal energy storage tank. This is a 5 million gallon tank which stores 42°F chilled water to use to offset peak electricity costs between 11 a.m. and 7 p.m. In the future, the chilled water from the Central Energy Plant will replace distributed chillers across campus, providing building cooling needs. And it also uses extremely low global warming potential refrigerant compared to the legacy chillers on campus. If we step inside the plant for just a minute, here we can see the steam turbine generator, and this is where we can send steam to generate additional electricity. And the condensing heat exchanger utilizes hot water return from Ford campus to condense the steam exhaust while generating free hot water for campus building heating. If we step back outside, underneath the parking lot and the walkways, we see the snow melt system. And this has been a big win for us operating in the last year because we can reject additional waste heat from the steam turbine generator to the snow melt system and offload the cooling water towers. And we're estimating about 2 million gallons per year of water savings. Finally, on the west side of the plant, we see some of the condensate tanks. And as you may know, condensate return is really important for the energy efficiency and water use associated with steam production, with higher condensate return being better. And our plant sees about 85% condensate return. So go ahead and next slide, please. And here you can see the progression of the plant over the last few years from design, construction, and operation. So on the left side, we have the 3D model of the HRSGs. And this is part of a larger 3D model of the plant. And it's actively used as part of a digital twin, which acts as a repository for design and equipment records, live operating data that operators can actually access while they're out and about in the plant with augmented reality. And in the future, advanced analytics, pattern recognition, and predictive operation. In the center, you can see the combustion turbines and the HRSG staged in place. And a large majority of the components for the plant were prefabricated off-site and then put in place, which is a lot of the success during construction. And then finally, we have the HRSG in operation with the combustion turbine towards the left of the picture, the HRSG in the center. And there is a duct firing control skid towards that center there, which can be used to boost steam production if needed. We really hope that you can come visit this amazing facility in person in the future.
That's awesome. Thanks, Michelle. We really appreciate it. Folks, if you've got questions, go ahead and type them into Slido, and so you don't forget them, and we'll try and get to them. So thanks again, Michelle. I'd like to now turn it over to Jim Henry. Jim is the Global Compliance Manager at Iron Mountain Data Centers. He manages compliance with various international standards ranging from energy and environmental standards to information security, business continuity, and cybersecurity. Not a small job. So with that, Jim, go ahead and take it away.
Awesome. So I'll echo Michelle's comments that hopefully in the near future, we're able to get the DOE team on site at one of the data centers. Hopefully my favorite one that I'm going to talk about without being too biased. Just a quick brief overview of what a data center is for those of you who may not know. Anytime new software applications or technology is developed, it's got to live somewhere, right? When you have a cell phone, when you have a computer, you've got a data center problem somewhere. We are the cloud is what I often tell people. There's a couple different types of data centers too, and that plays into an important kind of part in the Iron Mountain story. You have data centers that are totally proprietary. So those are the ones that, you know, some of the folks on this call, you might have like a data center in like the basement of your office building or in your closet. You know, those are tough to keep efficient when they're in your own building. There are total cloud data centers, right? Large cloud providers that, you know, your Google Drive and everything, those live in proprietary data centers where the IT equipment, you know, all the racks and servers are controlled. The hardware, software is controlled by who owns the building. And that makes it a little bit easier on the energy efficiency side. So I'm a little jealous. But then in the corner, there's co-location data centers. And what a co-location data center is exactly what it sounds like. You're co-located with all kinds of other industries. So in the photos we're looking at right now of Kansas City, there's that bottom left-hand corner. So if we were standing in this room today, right now that room would be filled with servers, cages separating those server racks, right? Co-located together, banking industry, healthcare industry, government, streaming, entertainment, right? So there's all sorts of things. We don't actually own the IT equipment. We rely on our customers to make decisions about what they need, move their gear in, and we make sure it's always on, always secure, and always sustainable. That's kind of our goal. So with that said, the way that we operate is largely in hand with reducing the overhead in that equation that is between our customers' utilization and then how we cool it, what we need to do to power it and make sure it's always on. So in the Kansas City data center, the photos you're looking at right now, you're seeing a couple things at play. mainly just looks like server racks. If you've seen one data center, you've seen them all. But in Kansas City, unique to another one of our sites, it's actually underground. So we have 2 underground data centers. This is a smaller, much smaller one, but so the ambient temperature is about the same year round. It's agnostic to the seasons. But no matter what in a data center, you have air moving around. So in Kansas City, we've done large retrofits for LED lighting. We've done a lot with air management, making sure floor tiles, like you see in the photo, are put in the right places. That hot and cold aisle containment is actually set up in the data center. And then, of course, that's an iterative process. So when we talk about projects, and I'll talk, kind of through this as we go through the slides, you're really never done in a data center. You could move a chiller plant in, right? You could update some infrastructure, but still you're never really done because conditions always change. We're not manufacturing anything, right? So it's not like we have a steady assembly line or we have a steady kind of schedule that we can follow. IT gear has peaks and dips and everything else depending on processing power. So you're always dealing with all sorts of things that make this an iterative process. Next slide, please. Again, this one is not underground, and it's a very new facility. This was built in 2017. This is Northern Virginia in Prince William County in Manassas. This is a large data center. It's actually a campus that's built out for 4 buildings. In this data center particularly, when you have a new building, and this is a struggle I think in any industry, you're like, where do we start? All this infrastructure is new. There's no antiquated capital, like projects that we need to do, and everything should be working as appropriate, right? So, we assume that too. And of course, as we have customers filling up these large rooms like you see in the bottom left, and we've got these gigantic buildings, and by the way, just in case anyone was curious, when you have a data center and you see those windows in that middle photo, you really only have windows in office areas. If it's a high secure facility, which all of our data centers are, in the actual computer rooms, you can't have windows. It's an added risk that you really don't want to introduce to the environment. So with windows and things like that, these are totally closed rooms. So and all the infrastructure was brand new, the static switches, all of our substation gear, the chillers, the air handlers, everything was brand new. So what we did was strategically deployed our customers in ways where air management from the jump was taken care of. So if our customers were running very dense loads in their data center racks, we didn't wait to put cold aisle and hot aisle containment in. It happened from the beginning as a best practice. And then we tuned the building management system to meet the demands of the load data hall by data hall. Not only that, but some of the other challenges we found was that some of our customers had legacy IT gear. So if you're familiar with a server or a switch, you see things blow front to back. Some of the gear was blowing side to side. So we utilized kind of an opportunity here to create custom ducting and ductwork for the data centers. And then lastly, we've also engaged an AI company to run the data in our building management system, because since everything is new, we wanted to see how we could optimize our operations. Next slide, please. And I've only got a little bit of time to talk about this one, but it's super neat. So I'll just talk about the one focus. This is the Western Pennsylvania data center. It's north of Pittsburgh. This is actually about 20 minutes from my home. It's near and dear to my heart. At this site, we have an underground lake. I'm not kidding. We're 280 feet underground. The lake is part of the Pennsylvania Natural Water Table. It's completely segregated. It doesn't have any inflow or outflow. Rainwater doesn't affect it. It's about 57 degrees year round. And we utilize that to cool the first phase of the data center. So it's a closed loop system. We also utilize free cooling in the wintertime to bring in cold air. And then of course in the data center itself, in the small photo that you can see in the bottom middle, we utilize cold and hot aisle containment in addition to all of these efforts and tuning the building management system to really maximize the power utilization effectiveness of the total site. So, there's a lot of unique things about data centers, but to put a bow on it, data centers are a massive user of electricity. So not only do we purchase, meaningful local renewable energy from various projects and suppliers, but we also understand that the greenest kilowatt is one that isn't even used. So even though we're buying renewable energy, and we also generate on-site renewable energy at some of our other sites, we also aim to use all of that renewable energy in the most responsible way possible. And with that, I'll kick it back to Maria.
Awesome. You know, despite the fact that I've seen these tours already, I'm still taking notes. So I was just thinking the underwater lake surely would be an in-person site visit. Many of us, I'm sure, not only on the panel, but that joining us today would like to do. So thanks so much, Jim. We appreciate it. So folks, if you've got questions for Jim or Iron Mountain Data Centers or any of the work that you just heard about, please feel free. I know some questions are coming into Slido, so please feel free to send your questions and we'll get to as many of them as we can. So thanks again, Jim. Okay, and now our third virtual site visit is in the state of Maryland. David St. Jean is here to talk to us. He's the Director of Energy and Sustainability at the Department of General Services for the state of Maryland. His office purchases all electricity used by the state government. He manages the state energy performance contracting program, chairs the Green Purchasing Committee, manages the state energy database, and is the go-to office for state agencies on energy-related matters. So as you can imagine, quite a large portfolio, lots of things going on. So, you know, you've got David here, so feel free to ask him questions. So David, we're going to start with a quick video on the state of Maryland's work, and then we'll turn it over to you. So if we can roll the video, that'd be great.
Thank you for that introduction, Maria. Actually got kind of tired listening to all the things you do in the office. It was exhausting. I think I want to retire tomorrow.
There you go.
It's tough to follow a presentation with an underground lake and an underground data center, but I shall do my best. I guess just briefly, we'll talk for a minute about our participation in the Better Buildings Challenge, because a lot of, if there are any other state participants on the call, everyone always wants to know, how do you save energy in state buildings? How do you get management behind it, et cetera? Part of the solution was, I think, joining the challenge, because that got management more interested in what we were doing. And when we joined the challenge, we joined it with 9.8 million square feet of state buildings, 69 buildings. And most of these savings were achieved through energy savings performance contracts. In particular, a couple of state hospitals did exceedingly well. One of them, a 1 million square foot hospital, saved 55% over their annual energy use. But even without that, there was an 18% savings overall through that portfolio. So it's been a very good experience for us, and I think it motivated us to achieve even greater savings than we would have otherwise. Thank you. Can you go to the next slide? Yes, so let's talk for a minute about the railway station itself. As you saw from the video, that station is over 100 years old. It was built in 1853. And at the time, this is Cumberland, Maryland. There's, if anyone has heard of the Cumberland Gap, there's a gap in the Appalachian Mountains that where three major transportation routes went through that area for anyone traveling from the east to the west, from the mid-Atlantic states. So there was the National Railroad or National Road there, which was America's first highway, the B&O Railroad and the C&O Canal, and then finally the Western Maryland Railway Company started in 1853, built the railway station in 1913, and it remained as a passenger terminal until 1958. So this project itself started, I guess it was around 2012 when I got a call. I was working at the Maryland Energy Administration at the time as a program manager. And I got a call from the director of Canal Place complaining about HVAC equipment that was falling apart, very, very drafty buildings. You imagine it's 100 years old. There was virtually no insulation. The windows were all single pane windows, wooden windows that leaked air year round. They had humidity problems. It was a bit of a mess. The building had been upgraded in 2000, but I think they did sort of a bare bones upgrade. They put in the HVAC system at that time. So at the time we had a Department of Energy grant to hire auditors, and we sent some auditors up there to look at the building. And they came back with a report talking about an HVAC system that was at the end or beyond its useful life, leaking refrigerant lines. As you can see in the picture on the right, all the outside units were corralled into this little tight spot because it's an historic building and there was limited space where they could be put. So there were a host of problems. And at the time I ran a loan program at Maryland Energy Administration that helped finance these energy efficiency projects for state-owned buildings. So we were able to pull some financing together. I went out there and addressed the lighting problems. We pulled out all of the existing HVAC equipment, which was a challenge, obviously getting all the refrigerant lines back out of the building, putting new ones in, and maintaining the historic structure itself. And we also right-sized the HVAC system because, like most HVAC systems, it had been oversized by a considerable amount. So we used the MEA loan to address the insulation and lighting improvements. We used some other capital money to put in the HVAC system, and the final result was a 21% annual energy savings and a $12,100 a year annual cost savings. And we did all that while the station was still in operation. So it was minimally invasive, I think. And I think the end product, they have a much, much more comfortable building, and it is running much more efficiently. And thank you. I think that's all I had to say.
Awesome. Thank you so much, David. I appreciate it. Again, I'm over here taking notes. So thanks. So now we're just going to open it up to the Q&A part. I thought we'd start with our, what's the word I want? Sort of the lightest question we got. Jim, someone wants to know if Batman lives in Western Pennsylvania. So
I do live 20 minutes from Boyer, so yes, Batman does live in Western
Pennsylvania. So there you go. I just thought there you have it. Okay. So now I'm just going to read through some of these questions. Some are specific and some are for all three of you. So with that, Michelle, a question for you. And that was if you could explain the concept of digital twin. People were interested in exactly what you mean by that.
Sure thing. So the digital twin is almost like a model or a virtual representation of the plant. And there's different components to it. So we took the 3D model that we used during design phase. So it has, detailed engineering design of all the equipment. And then we layered on top of it live operating data that operators can access out in the plant even. It also has the work order and maintenance system layered on top. And in addition to that, some of the analytics and predictive operations are going to be coming soon. So for example, looking at weather and bringing that into the plant to see if anything needs to change. For example, like putting smart sensors on our steam traps that notify the operators when those steam traps fail so that they can immediately go out and fix them instead of, waiting many weeks while that steam trap is failed and you're losing the energy efficiency there.
Thanks, Michelle. See, the drag about virtual is that I can't turn to the person who asked the question on Slido and say, got it, but let's hope. I think that answer was great. So thank you so much. Jim, a couple questions for you. One, pretty straightforward. If you can explain what's a hot, cold aisle again. And then I think there was another question. Let me just read it to you. See, part of the challenge that I have to scroll here. But I thought that was interesting too. So I'm going to give you two questions at once. Hot and cold aisle, if you'll just describe what that is again. And then this was another question for Jim. Was the Pennsylvania DC location a data center? I'm like, why not Washington DC? Okay, was the Pennsylvania data center location chosen specifically because the lake was there? Question mark. How do cost savings from this facility compare to those without a place-based temperature regulator? Great questions. So hot and cold aisles first, and then a little bit about the Pennsylvania location.
Awesome. So yeah, hot and cold aisle, basically what that means is that when you're looking at a data center, let's just say it's a closed room, you don't want hot and cold air mixing with each other, because then that return air that has to go back into the cooling system is just making the cooling system work harder, and then you'll have to ramp up fan speeds and your infrastructure is using more electricity. So if the air that is actually moving up into the servers is cold, and then it doesn't mix with any hot air there, then the coldest air is going into the servers. And contrary to popular belief, data centers can be like 80 degrees. They don't need to be super cold like most people think. So cold air comes up, gets sucked into the servers. Then the hot return air can go back into the plenum. And it's all that air mixing together is not really great for the equipment. It makes it work harder to use more electricity. So when you start actually segregating that air, you're running a more efficient operation because it's not mixing together. And then you're basically, when you look at building a data center, you should be using like computational fluid dynamic software to see where those what those hot and cold aisles look like temperature wise. And then that can factor into kind of what Michelle was describing, where you have a digital model of what temperatures that actual center or building's running at, so you can tweak the building management system, tweak your chillers, and then tweak your infrastructure to make it maximize and use as low amount of kWh as possible. And then on the data center side, I would normally say that yes, the location was chosen, but Iron Mountain already owned the property. So Iron Mountain is an information storage and management business. We've been around since 1951. We've got over 1,500 facilities globally in 50 different countries, but the data center division is much smaller. So we already owned the mine. It's a retired limestone mine in Western PA for records management. And when we got into the data center business back in the early 2010s, late 2000, like 2009, 2010, it was a natural choice to put that data center there by that lake because we could use it for the geothermal cooling system. And yes, I mean, obviously we do have more energy savings than a traditional data center because we don't have to use additional infrastructure like an additional chiller plant in place of that. And we're also in Western PA where it's really cold in the wintertime and in the spring and fall, so we can use the free cooling. Now, what I will say though is that as data centers, our mission is to scale, right, as technology advances. So savings are subjective. You may have really good savings from a project, but then just by iterative design, you're adding more infrastructure. So then you'll actually be using more electricity, but it's really about bringing the delta between total facility utilization and IT utilization as close as possible.
Awesome. Thanks, Jim. I appreciate it. Okay, here's one for David. David, the question said, if you could just elaborate quickly on multiple grants and fund sources and how they fit together. That's the answer, right? No, just kidding.
That is the answer. That's pretty close. Well, it really depended in this case, the fund balance in the loan program at the time, the timing of it at the time, We have a couple of different programs in Maryland for zero interest loans for state buildings. And then there's always state treasury lease money available for capital projects. And then of course, general funds generally as a last resort. But that particular project used the zero interest loan money from MEA for the lighting and the insulation and air sealing. And then the capital funds went into the HVAC replacement. Because the HVAC had gotten so bad that before the whole project could be pulled together, it ended up being an emergency replacement. So it ended up being capital funding.
Great, thank you. Okay, this one is the top, one of the two top voted questions. And this one is to all three of you. So you can pick who goes first. If you could do this project all over again, what would you do differently? Actually, the question is, what is something you would do differently? But I decided to just riff on that as the moderator and give you a little bit more flexibility. So there you go. Who wants to start on that one?
I can start doing this because it's a simple project, pretty simple answer. I think doing it differently now, looking at the state's interest in decarbonization, electrification of its buildings, I would probably model a VRF system and see how that could have been worked out into the scope.
Cool. All right. Michelle, what's one thing you would have been done differently?
Well, for this project, we had a lot of really strong collaboration between DTE Energy and Ford Motor Company and the architecture and engineering company that was involved. And it was really beneficial to have the end, like the future plant operator involved in the design. So maybe that doesn't quite answer what we would do differently, but we would recommend that if folks want to do that, it results in a really good product at the end.
So you were pleased with your process. So, okay. All right, Jim.
Yeah, it's an interesting question from a data center perspective because I've got 3 data centers and one of which is kind of a constant project. So I'll just talk about that one. When you build a data center, of course, every couple of years, there's better infrastructure that comes out as far as chillers and computer room air handlers, pumps, more efficient infrastructure. So even since we've built the data center in Manassas, there have been advancements in some of the cooling infrastructure that's come out. So it's not like we could have changed anything in the design process then, but of course you can always make upgrades. And really, like I said, the Western PA data center is always a project because you're looking at lake temperature, you're looking at tuning that system to meet the demands of the IT equipment in the data center. So really, it's about just making sure that we're staying on top of that at scale and tuning it over time, which, a lot of that revolves around we have a dedicated data center kind of like operations management team. Aside from the folks who actually run the data center, the folks who run the building management system are kind of looking at ways that they can optimize. Really, it's all about data, making the data available to our technicians in the data center at any given time so they can look at all of the temperatures, all of the levels of the water temperature and things like that, and tune it according to what's going on inside and outside. So it's kind of an iterative project. We're always doing things differently. It's a project that's never done.
Interesting. Okay, great. Okay, Michelle, I have 2 more questions for you. I'm going to do what I did for Jim, which is crush 2 questions into, so just take notes. Here are the 2 questions. What is the low refrigerant at the chillers at Ford? That was one question. And then the other question was, for Ford Central Plant, do you use any off-the-shelf software to develop the 3D model, or do you custom develop, or is that a custom developed program built specifically for Ford?
Okay, so the refrigerant, it's called R1233ZD. I think it was mentioned in the video, EcoWise refrigerant. It has a GWP of 1. And if you compare that to like R11, has a global warming potential of around 4,000. So it's significantly lower potential environmental impact. Regarding the other question about the digital twin, I don't know, but I have Jeff on the line as my backup, and he might be able to answer that question.
That's great, Michelle. You've done great so far. So the digital twin that we used is standard off-the-shelf technology in its beginning, and that was generated using AutoCAD and Willow and a few others, all mashed together. As we've gone into the operation side of the equipment, it is a custom package. Ecodomus is a developer that does similar types of stuff. I don't have permission of the the company to put their name out there, but so I won't name them specifically. But it is custom because it is a powerhouse that is an electric utility that is regulated. So I don't want to get in trouble with the regulators by putting things out there that maybe I shouldn't. So
We don't want to get anybody in trouble. So
no, we don't.
all right, that's great. Okay, great. Now a couple more questions for all three of you. Because I think this one doesn't make it clear as for all three of you, but I think it has to be. How long before you break even in terms of the extra capital costs, the electricity and the water savings? I'm going to let you all decide who takes that. Jim, you just did a big breath.
Yeah, that's a tough one. If I'm
And it
thinking,
depends, right? Lots of depends.
it really does. I'd like to say that we've probably more than broken even, because of, well, without getting
We don't
into
want to get anyone in trouble.
right, or yeah. But as far as return on investment, the lake really makes things easier, right? We're not really, we don't, the return water comes in and then it kind of naturally rejects heat. The lake rejects heat. So we're not actually having to cool that water back down. So that's kind of nice. So as far as a chiller, like if you say lake versus chiller, it would take a longer time to get an ROI out of a chiller, whereas the lake I probably paid for itself like multiple times over. But then again, there's more than just that data center running on the lake, and we have another phase of the data center that runs on a chiller plant because the lake can't do the entire data center. It's only part of it. So, as a full data center, I think it would take some math to do, but I think the lake in itself, if everyone could land their facility next to a lake and, do geothermal, yeah, of course you would, right? Or if you had a fjord in the Nordics where you can use free cooling and then use a fjord to cool your data center, of course you would. But that's just not reality, so.
Okay, Michelle or David or Jeff, anybody want to weigh in on how long, I have to read the question, how long before you break even in terms of the extra capital costs and electricity and water savings?
Well, I can talk about that a little bit for Ford. This central energy plant is it's being built, or it was built to provide services to the renovation of our new campus. So we're presently, the idea of building a central energy plant started, as I think the video said, about 5 years ago. And when we started announcing that we were going to completely rework and redo our campus. So there's about 25,000 employees, and there's several different chiller plants that I can tell you that they were 50 years old, plus or minus. And the idea that you've got 50-year-old equipment and you want to provide a good working environment to attract new talent coming out of college, et cetera, you got to have good, robust equipment. Not to mention that obviously testing is a very important part of rolling product out for Ford Motor Company. So replacement of old chiller systems was mounting up into the $50 to $60 million category. So there's an avoided cost there. And then not to mention the fact that they were distributed around the campus, and the efficiency of distributed chillers that were designed 50 years ago is pretty far up there. So in simple payback, I know, Michelle, you did a little bit of study on answering that question. As Jim said, it's a very difficult question to answer. When you're building new infrastructure, why do you build new infrastructure? There's a lot of reasons. Cost savings is one of those. Cost savings is not the reason that we built this central energy plant. So, we shut down a lot of old chiller equipment. We eliminated a lot of old refrigerants that have, you can't even buy them anymore because they have greenhouse potential issues with them. And we're shutting down a steam plant that was built in the 1950s. And yes, it's an Albert Kahn designed steam building, and it's the landmark in the Dearborn area. And yes, we'll have to figure out what to do with the building, but functionally as a steam producer, it's gone. And instead of burning a BCF of gas as direct emissions, we're now reclaiming that BCF of thermal load and supplying it to the campus as a heat recovery activity. So those are the reasons.
So I think, because it's hard, because I think people are looking for answers, like how long of a payback, and I get it. I think maybe, David, I can let you respond too, but I think there's two things going on. And one is actually the next question people are asking, which I'll get to in a minute. But I think the other question is understanding what sort of payback periods, is it months, years, or decades that your organizations are willing to, I was going to say stomach, that's not right, willing to endure or willing to live with, or, so I think that's part of the challenge here. So David, let me just let you respond, or Michelle, if there's anything else, and let me get to the other question. I think that's sort of getting at the heart of what y'all are talking about in a second, but I don't want to cut off David or Michelle, who might want to have feedback on the break even question. How long before you break even?
Yeah, so I think the question was additional capital costs. So I would define that as, the HVAC system had to be replaced anyway. So the additional costs were running load calculations to right size the equipment, and the additional cost was putting in above code HVAC equipment, right? And LED lighting. And so if I was going to look at the payback for the additional cost for all those items, I'd say 2 years. Very quick payback. I mean, if you're looking at the actual payback from installing a brand new HVAC system, I mean, it's going to be really the life of the equipment probably, or beyond, right? Because it's a very capital expensive project, but it's the additional cost really that we need to spend on more efficient equipment that is a very easy to pay back item.
Great. Michelle, did you want to add anything to that question?
Sure. Just in terms of some of the components of the central energy plant, for example, the thermal energy storage tank, we consider that as having a less than 3-year payback. And some of the optimizations that we've done since the plant has been operating, like with the snow melt system and with an RO feed water preheat heat exchanger that was put in, those have paybacks of 6 months to a year.
Okay, great.
And I'll just add to that,
yeah, please.
In general, I've been in this job for a little over 25 years, and in my career, I've been responsible for performance contracting as our primary delivery for energy efficiency projects. And those projects span the gamut of compressed air, HVAC, and lighting for the most part, if you had to develop 3 buckets. And the lighting projects, you go back 10 years ago, they would fall into the 3 to 4 to 5 year simple payback. And then today, because we've done so much lighting upgrades, it's in the 4 to 6 to 7 year simple payback, just because the low hanging fruit is gone. HVAC is very difficult. It's always been a 7, 8, 9 year simple payback, and then compressed air is falls into the same category. So we do a lot of performance contracts in the 6 to 10 year contract term, and that covers all of the installation, financing, overhead of delivering that project and delivering those savings.
Interesting, helpful, really helpful, you guys. Okay, so this is one, and I'm very mindful we have less than 10 minutes to go. I know the hour goes by fast, but I think this one sort of gets at the heart of some of the questions, and I think a little bit about what you all talked about a little bit, but that was, how do you balance sustainability, resilience, and security in your buildings, right? So it's monetizing some of the stuff like secure. I mean, that, okay, I'm not going to riff on this, but let me just read the question and let you all answer it. So how do you balance sustainability, resilience, and security in your buildings? Can you speak to a few examples of these themes at play in your decision making? Right. So some of you have already talked about, we had to install, David, I think that was you, we had to install a new chiller anyway, right? So then the question is, but let me not pontificate for you. Let me just ask you guys the questions. Who wants to take a run at a couple examples of the themes of sustainability, resilience, and security, and how they compete or don't, or get balanced as you make these decisions?
It's a particularly interesting conundrum in data centers that need all three. Certainly, and I mean, in the manufacturing industry too, you're also looking at those things as well. So I'm interested to hear what the others say. But I mean, so yesterday, ironically enough, the Better Buildings session that I spoke on was about resiliency and how it crosses with energy efficiency. So in data centers, obviously, you know, Michelle, I'm not sure who you guys have your data center with, but it's probably co-located somewhere in some capacity. And if it ever goes off, that's not good for you, right? Because that's probably what's running part of your business, right? And same with, you know, the state of Maryland, right? You know, David, you guys probably have servers sitting somewhere other than maybe some proprietary stuff. So for data centers, staying on all the time is primary. Everyone in the business, period, even providers that don't do green things or participate in sustainable practices, their number one focus is going to be staying on all the time. And we build that around service level agreements, because everyone hates when they go on Netflix and it's not working, right? We hate the buffering, the wheel of death, right? So really it comes down to like in the video, you saw that Iron Mountain data centers were 50,001 certified, 14,001 certified. Well, we're also certified in the most industry information security and business continuity certifications in the industry. So we're, you know, if anyone on the call has heard of 27,001 or NIST 853 for the folks in the government, or FISMA High, or PCI DSS, HIPAA, right? So we are scrutinized on all levels of security for data availability, processing integrity. So basically what that means is they're all equal for us. It's always going to be secure, on, and green. So balancing the sustainability with the resiliency is a little interesting, because you've got to have diesel generators for backup, right? We don't like emissions. We don't like diesel. So as an industry, and I think this will hit other industries like maybe the hospital industry in a while, we're looking at more of a model where could we go to hydrogen for backup fuel, right? Another thing we think about all the time is, you know, we have UPSs, uninterruptible power supplies. We do have to have, block redundant systems so that if one fails, or if a PDU fails, that there's a static transfer switch that can transfer over to the next, redundant block, and then a redundant generator in case a generator doesn't fire. So there was a diagram in my presentation yesterday that described just that, how redundant the systems are. And then of course with security, I think it's a little bit off to the side. Security doesn't really inhibit sustainability or resiliency for us. We have to be the most secure facilities in the world. I mean, period. This is where healthcare data, personal data, banking transactions, intellectual property, it all lives in the cloud. It all lives in data centers. So there's no compromise. I mean, it's primary just as the other two are. It's super important.
Great. All right. Thank you.
I'll add on to that. And
Go ahead.
The resilience question is hugely important to many companies. And yes, we do have a data center, and it's a very large data center. And when we built it, we went to the utility company and said we want 2 fully redundant 120 kV supply, and we have diesel generators to back it up, and we have UPSs to make sure it's online. And it's really the same question when we built and went after the design intent for the central energy plant. It is fully capable of black start and island mode operation. We have 40 megawatts of diesel generators on standby, integrated with the central energy plant. Actually, it's 30 megawatts integrated with the central energy plant, and it's fully capable of black start and island mode operation. And that's because, you know, if our research center goes down, it's millions of dollars a day. It's actually more than that probably, but it's a lot of money.
A lot of money, right? Right.
If something goes wrong there.
Right.
Michelle, I don't know if you want to add anything else to that.
No, you covered it, Jeff. Thanks.
David, how do you balance sustainability, resilience, and security in your buildings?
Yeah, so I struggled with that for a second. I thought, well, I don't know, is that really a problem? And then I remembered, wait a minute, we're negotiating a performance contract at a correctional facility in Hagerstown right now. So obviously their primary concern is keeping people on site. And, you know, if the electricity fails up there, doors start opening, lights go out, bad things happen. So layering performance contract and energy efficiency initiatives and ECMs on a site like that is definitely a challenge. We've been able to dangle the financial advantages of doing it. And also it's a good way for them to address lots of items of deferred maintenance that, you know, you have to go begging to the legislature to get some pieces of equipment replaced. But if you can get them done through an EPC, it's much, much easier.
Interesting. Okay, really quick, because we have 2 more minutes. Michelle, can you do this really fast? But I feel like this person asked early and I want to make sure. Can you, Dearborn, that's you guys. Can you confirm that the snow melter for heat rejection to lower load on the cooling tower, even when there was no snow to melt, a very shallow ground heat sink?
Yeah, that's essentially what it is. Yeah, and we're planning to use it year round, even when there's no snow.
See, well done. Okay, well, I'm nervous that if we go to another question, being that it's 1:43, that we will run over our time. So I think we're going to call it there. Thank you all for being here, attendees and panelists. We really, really appreciate it. And Michelle, Jim, Jeff, and David, we really, really do appreciate it, not only for today, but for stepping up and helping us try and be creative about, during a pandemic, how we were able to continue our desire to shine a light on the work that you're doing and share it with people, and sharing your expertise and your learning, and even sometimes the things that didn't work, although I didn't hear many of those today. So kudos to all of you, but really thank you for sharing the work that you're doing and continuing to share what you're doing, and your expertise and thought leadership, and really what not only you're thinking about, but what you're doing at your facilities. So thank you to everybody today. Thank you again to Ford, Iron Mountain, and the state of Maryland for hosting virtual site tours and doing it twice, earlier in the year and then bringing those virtual tours to the summit. We all really appreciate it. With that, thanks everyone. We appreciate it. Hope you enjoy the rest of the summit sessions today. Thanks. Bye-bye.
Thank you.
Thank you.
Bye. Thanks for having us.
You bet.